that. And I'm going to share my screen. Okay, so hopefully you can see that big blue screen saying large area hearing loop systems, fault finding. So effectively what we're going to cover today is the type of loop faults that you commonly are going to get, the tools that we can use.
It might just be me,
Come
James,
up
but
on
you
the
appear to have frozen there. Okay, you're back. Great.
okay. What I will do actually is I will maybe switch, see if I can switch my video off. So and then we'll be looking at the fault messages that come up on the drivers, both the V Pro drivers and the V Plus drivers, and kind of like tie in basically what the message means and what it relates to as far as the fault is concerned. And as we go through the presentation, we'll be actually going over the kind of the practical methods that we would use and assisting you in finding the faults. Also on the webinar today, we've got Dave Scroggins, who's provides fantastic technical support for our guys over in the States as part of Contacta Inc. And so, Dave, if you want to dive in at any point in time to elaborate on anything that I've said, by all means, do so. Also, just for participants that we've got on the call, if there's any questions that you have, to be fair, it's entirely up to yourself. If you want to just unmute yourself and jump in with a question if it's pertinent at the time, or you can leave until the end of the session and ask it there. There's also the chat as well. So I think James is going to be monitoring the chat if there's any questions come up there. So when a loop layout is installed, there are a number of faults that can occur.
Sorry to interrupt, James. Just because of a signal, you mentioned you were going to turn off your video to make sure that the sound was a little clearer.
All right, let's see if I can. There we go. Yeah, hopefully by turning the video off, that will make things a bit clearer. So when we basically the basic types of faults that are going to occur are a break in the loop where it's been cut or damaged, or a short between phases. For example, with a phased array system, you may, especially with copper tape, you may have a short taking place between the two phases. We have ground faults, which can be quite common. This is where the loop actually is connected to the building earth. For example, an example of that would be if the like a nail going through the floor, and also making contact with metal ground and the loop as well. So you have a feedback circuit being produced there. And then finally, we're going to talk about induced ground faults, where there's not actually any physical connection between the loop and something else, but it's the current induces a feedback current through the earth. But we'll go elaborate that more as we go through the presentation. So just to elaborate more on what I've just said there, the break in the loop, but what we want to do is we want to check the continuity of each loop or array. and it should only be a few ohms. Later on in the presentation, we will show what these values will be, but typically you're only looking at sort of like, anything between 2 or 3 ohms up to, maybe 10, 12 ohms or so is the value that you want for a good working loop. Obviously, if it's any higher than that, or open circuit, then you have a cut, a break in the loop, but you need to find out where that is. Another problem that you can have is a short between phases. If you've got a phased array system, then you have the problem of one phase shorting out with the other. And we'll show you how we can resolve that as well. Another common thing, as I mentioned, was a ground fault, where you have the loop connected to the building earth, and we have a process that we can go through to methodically find where the location of that ground fault is. And then finally, we'll cover a little bit about induced ground faults as well. Regarding diagnostic tools, basically, I've only mentioned two pieces of equipment here that are quite useful for having in your tool bag on site. The first one is a high resolution ohmmeter. So basically what that is that it kind of has a high resolution of about 200 microohms, which means that it can measure small, very, very small differences in resistance. And we'll show you why that's important with finding out the location of a fault. Another piece of equipment which is variable in reliability, but it is a useful tool to have nonetheless, is a cable tracker or a sniffer tool. I'm quite sure many of you are probably familiar with this piece of equipment. It's not particularly expensive, but effectively it's made up of two components. You have a tone generator here, which you connect to your loop, and then you have a probe, battery-operated probe unit here that effectively picks up the tone. And we'll show you how that is implemented in the fault finding of the loop. So, first of all, we're going to talk about what to do when you encounter a break, a cut in the loop. So it can be caused by a poor feeder cable to loop termination connections. So that would be the first point of call to check. Check the terminations. Check the mention here that check the NL4 connectors that are connected in the back of the driver. They may have been connected incorrectly. Because if you connect like two pluses or two minuses together with the NL4, then you'll effectively get an open circuit. So what you want to do is check that's a simple thing for you to check. If it is an actual cut in the loop itself, then you can use the sniffer tracer tool, which is quite a easy, quick way of checking the loop. Or a more reliable method, if the sniffer doesn't work, is to use the high resolution multimeter with an extension lead. So let's look at an example where we're using the high resolution multimeter or ohmmeter. So let's examine the circuit first. So we've got the perimeter loop here. We can see that we've got a break in the loop at this particular location here. So you've got your long test lead extension loop here. And effectively what you're wanting to do is you're wanting to have your test lead here and basically just check all the way various points along the route until you eventually get a short circuit. So here, for example, we can see that this point here So here we can see that we basically use the lead here to trace along the route of the perimeter loop until you find where the break is. So for example, from here, you're not getting anything, it's open circuit until you get to this point here. And as soon as you start probing at this side, you will get a continuous loop. So you know that at this point here, that's where the break is. So that's effectively how you find a break in the loop using a millimeter. Quite often the meters now have a tone. So effectively, when it makes a continuity tone, you know that you've got a good connection. So if we were testing all the way along this point, you're not getting any tone at all. And then as soon as you hit this point here, you find that you're getting a tone, and that's the point of the break. Using the cable tracker or sniffer tool, here we have the transmitter. Now the transmitter has two leads. You leave one with no connection, and the other one you fit to one of the tails. It doesn't really matter which tail it is, but one of the tails of your loop. And then you use your probe. Now, most probes now have the option of being able to plug in a set of headphones, which allows you to hear better. And you're effectively just listening for the tone. When you're getting the tone, then that means that the current is flowing along here. When you're probing on this section, you're not getting any tone. So you know that this part is not being fed by the loop. And you basically just follow the route until you find this break again. So effectively, in my experience, I've found that it's down to a resolution of basically just a millimeter either side. Again, this normally happens with copper tape that's been cut by carpet fitters, for example. So when you're on this side of the cut, you're hearing the tone. On the other side of the cut, you don't get anything, and that's how good the resolution is with it. The downside of this is that this tone is actually quite weak. And if this is installed under very thick carpet, or even, if it's sort of like ceramic floor tiles or something like that, then the signal that you get through the probe is very, very weak and can be undetectable. In which case, this is when this method becomes unreliable, because you're not able to hear the tone. But if if it's carpet tiles or even just a standard perimeter loop around a room, then this works quite well.
Can I say something?
Of course, Dave. Yes, of course.
Apologies. Just before we ask, but I've just received a message from Tommy asking to be let in if you'd be able to, James.
Of course. Okay, Dave, carry on.
The cable testers that I've used and experienced, you have to connect one side of it to one end or the other of the loop, and the other end needs to be connected to earth ground from an outlet as a reference, and you get a very, very strong signal. It doesn't go away on the opposite side of the cut, but you can hear the volume difference from one side to the other once you pass over it. So that's how I've used them. Another situation is in a phased array. I've never had any success because every time you hit a turn in the wire, you have a dead spot from the tone being canceled equally between that 90-degree. So every time you hit a corner, you think that's where the cut is. That's not true, because it's canceling itself just like you would directly above a loop wire with a T-coil.
Okay. Dave, one way that you maybe mitigate that is that if you moved further away from the corner, would the signal come back? Would that be an appropriate way? Yeah.
It's when you're equally spaced between the two at a corner. it cancels out between.
Yeah.
Once you make the turn, though, it comes back, and it's very, very hard to find a cut in a phased array without using the continuity method, where you actually poke a hole into the flat wire and you have a continuity or not, and then you go 20 feet and do it again if you can find it through the carpet or can have access to it.
Yeah. Yeah. So moving on from that, the next problem that we have is short between phases. So again, the easy quick checks that you can do is to check your feeder cable terminations. So here's your termination here. There may be a possibility that these are shorting out for whatever reason. And then another point to check is where the primary and secondary loops cross over. There are, maybe the insulation has been compromised and it's causing them to short. Again, when you're measuring the resistance, you want the resistance between the phases to, they should be open circuit. There should be, it should be an infinite resistance. But you're looking for, a value of, greater than 10 mega ohms, which is, effectively, infinite resistance. That's what you're looking for. So just a diagram of that. When you don't, obviously there's not going to be any shorts in this area here. So when you're turning up to, for example, a loop that's already been laid, an existing system, not a new one that you've just installed, but an existing one, then you just need to worry about, lifting the carpets up the sides of the room here, and just checking these points where the two phases of are crossing each other, and that should resolve the problem. If just make a point of lifting the copper tape here and just putting additional insulation underneath, and by doing that with all these different points, you should resolve one of them will be causing the problem. You don't know which one it will be, but do one each in turn, test it until you find the one that's causing the problem, and then that's it fixed. Dave, is there anything you want to add to that? Are you quite happy with?
Well, a good product to use when you're installing the flat wire to keep a barrier between the two phases, or when wire crosses over another, it's called 3M 3903 vinyl duct tape. It tears very nice and straight and easy, and it puts a piece of thin vinyl between the two wires that you're overlapping or crossing. That's what's in that.
That's effectively what that is. Yeah.
It comes in all different colors, and one roll will last you a lifetime.
Yeah. Next thing I'm going to mention is the short to ground. So again, this is a bit more complex, and it can be a bit more difficult to resolve. But again, the resistance that you're wanting to measure between your phase, your loop, and earth, it should be infinite. There shouldn't be any connection between the two. If you're getting like kilo ohms, like 35 kilo ohms, or I think our drivers, for example, I think the threshold is about 100 kilo ohms. But if you're getting anything in that range, then it's showing that there's a compromise in the insulation between the loop and where it's meeting a ground point. I mean, the sort of the easy ground loops is where you've got a nail or something that has pierced the loop, and is actually it's a strong it's a short circuit effectively, and you'll be getting sort of maybe 10 ohms or 20 ohms or 30 ohms or 40 ohms or whatever. It's a lower, much lower resistance between the loop and the earth, and that's a reasonably easy thing to find, assuming that you can get access to the loop. But again, we're going to be using the high resolution ohmmeter and using basically probing around the loop root to try and find out where this is. So this is the diagram of the circuit. So again, we have our perimeter loop. This could be a phased array layout, for example. Here's our point where it's going to ground. Now you have, with your ohmmeter, you have one of the leads being connected to a good strong connection to the building earth. And then you have your other lead, which you then probe around the root of the loop. Now this isn't two leads. This is basically one position here, and then you're lifting the probe, and then you're probing here. Now, if we look here, this is the point here. When you're measuring your resistance with the ohmmeter, what you will find is that the measurement that you get for this point is going to be much less than the measurement that you get for this point. And effectively what you're doing is that you're kind of making a note of where you've measured, and you're kind of like subdividing your loop into manageable sections. And effectively you'll then say, for example, maybe then test here, and then test here, and then basically test again until eventually what will happen is that the value that you get for loop, position A and position B should be the same. Because basically you've hit this point here, and you're then measuring this resistance here, and you're not measuring the loop at all. And that is your point of where the ground loop is. And that's basically, I would suspect, probably the only reliable way that you're able to find where a ground loop is. Dave, would you like to make any?
No,
Yep.
that kind of explains it.
That's it. Yeah. Again, it's when you turn up to site and you're faced with something like this, it can actually be a bit of a headache, and it's not a 5-minute job. So just be aware of that. Don't think that you can be able to come in and within 15 minutes be able to resolve it. This can turn in.
Sorry, James, we've lost your audio there for a second.
Okay. Yeah, am I back? Yeah.
Yep, you're back.
Yeah. Okay, and so effectively that's how you cover or you resolve the issue of a hard short, a real short circuit to ground. A much trickier problem is if you get an induced ground fault. Now, one example of where you can get this is if it's becoming more and more common for metal stud walls to be used in construction. And if you say, for example, you've got a perimeter loop and you have it coming, see whether it's at floor level or at ceiling level, you can see that it's, the wire is very, very close to the metal structure here. And basically what that does is that the magnetic signal that's being produced by your loop is inducing a current in this nearby metal structure here. Another common sort of source of this problem is if you have the loop wire connected close to conduit or anything like that, anything that creates a path which is connected to the building earth can create this problem. This is a diagram that will hopefully explain this a bit better. So here you've got your loop driver with the loop current going around your loop. Now these orange wavy lines that's a magnetic field being produced by the loop. here we've got the metal clad stud wall, and you can see it's surrounding the whole loop area. This strong signal here is inducing a weaker signal in the metalwork within the building, and that is then feeding back to the building ground, which is then, because your loop driver is connected to ground as well, is feeding back to the driver. So you can see how you're creating this kind of like feedback closed loop. This is more difficult to resolve, and really the only way you can resolve it is to separate the loop away from, you know, the source, where it's a conduit or the stud wall or whatever, and really that's the only way that you can resolve it. I would say that you would probably encounter it more with perimeter loops, because you're using larger currents, and they're normally closer to the wall from the point of view of it's easier to install it that way. Phased array systems tend to use, you know, lower current values, and therefore they don't induce as much current in the in any surrounding infrastructure. But it's certainly something that it's a bit erroneous. It's kind of there's no hard and fast rules as to why it happens and what can make it happen. And it can, as a result, be sometimes a bit of a nightmare to locate. Dave, have you got anything you would like to add to that?
If you're in that situation where you're running a perimeter and you don't know, or you do know they have metal studs, your first clue is going to be, no matter how much current you pump into that loop, it doesn't get any stronger, because as much as you put into that loop, the metal absorbs it, and your numbers would be horrible. And then the only way I found to get away from that is install a phased array, and then you come in about 12 inches from the outside walls, and then you're not using as much current, and being 12 inches away versus an inch away from those metal studs, you don't have the induction going into the grounding of the building, and it does resolve the issues. But yeah, if you do a test loop in the middle of the room, it's going to turn out good. And then as soon as you run the wire tied up against the corners or the wall, you do your test and you go, well, what happened? Because now it isn't working, and that's the reason why.
Also, another good point with regards to the phased array is that for each segment, you know, that's up next to the wall, you find that the current is going in one direction and then it's going in the opposite direction. So kind of like the sum of them all kind of like cancels it out. So so that's another good, you know, good reason for using the phased array as opposed to a perimeter. But yes, it's something which does crop up, and it could be a reason why you're maybe getting some errors coming up in the drivers, because it's detecting this this ground loop. Talking of the drivers, we're going to start talking about what messages come up on the display, and kind of like what they relate to as far as faults are concerned. Talk about the vPro drivers to begin with. So if you have if there's a loop break, then the likely messages that you're going to get up on the display is primary loop resistance too high, or secondary loop resistance too high. And effectively, what you will then show is that, you know, when you select unlock the driver, you will get a cross being shown on either loop A or loop B to say that it's open. So effectively, you will go through the process of checking, your loops, making sure that there's continuity for each one. So typically, the resistance across the loops should be less than these values that we're getting here. This isn't impedance. This is DC resistance of your loop, and this is where these are the values where the effectively the driver kind of like says, "Well, stop. There's a problem here, and I'm going to say that the resistance is too high." In reality, these figures need to be much, much less than this, because you then have to think about the impedance, the reactive part of your loop, which is going to obviously increase the kind of the overall performance. So ideally, you're wanting values to be about sort of like 6, 7, 8 ohms for a good, working loop. So converse to the high, resistance too high, you'll then have another message that comes up in the vPro drivers where it says that the resistance is too low. Now, the reason for this can be, again, if there's a short somewhere, or if you're using a very, very short loop. So, for example, if it's a small meeting room, but it's got a lot of metal content within the floor, and you're using, a small loop, which has got a short distance, a short length, then the effectively the resistance of that loop is less than a quarter of an ohm. If it's less than a quarter of an ohm, the driver will knock it back and say, "No, I can't drive." Message coming up. Also, as a kind of as a safety mechanism, when it detects this, what we'll actually do is it will disable this particular output. So the driver can then still continue to be used, but this is like a safety mechanism where it will actually disconnect that loop. But just remember that that's the minimum resistance that we can use for the vPro drivers is a quarter of an ohm. That's for all of them. That's for the V22A and the V34 and the V34A. Also the V22 single output driver. It's the same. Now, as we were mentioning earlier about the ground, the induced ground loop faults, or even if it's a hard connection to ground, then what it shows up is that when it does its initial tests, when it boots up, it's measuring the impedance of the loop. And if the impedance seems to be extraordinarily high, then in comparison to what the resistance is, then it will say, come up with this message here, and it's likely due to the fact that there's a ground fault, which, as we have previously discussed, can either be an easy thing to resolve, or it can be more difficult to solve the problem. Just before we go on to the V plus drivers, Dave, is there any points that you would like to add regarding this?
No, I think you covered it.
Okay, thank you. The so the V plus drivers, they have a more basic display, but effectively the the warning or the fault messages that you get are pretty much the same. I actually think that these are probably a little bit more straightforward than the vPro driver messages, because it's pretty obvious. Loop A open fault. It means that it's detected that there's a cut in the loop for loop A or loop B if it's a phased array driver. And also a loop ground fault. So again, when it's doing its diagnostic testing, when it starts up, it's measuring the impedance of the loop as well as just the resistance, and it will flag up if there's something wrong as a ground loop. For the V22 drivers, you will get loop open or high resistance. So it actually says that loop open or high. That's what you get shown in the
Sorry, James, your signal cut out there again. We can't hear you, unfortunately.
Okay, I should be back. So with the V22, you get this message here to indicate that again the loop is open. And when we were mentioning earlier about the vPro drivers, with the V22, if you use too short a length of loop, or the resistance is too low, i.e. it's below 1/4 of an ohm. An example would be if, say, for example, you used, 14 gauge or 25mm wide copper tape to do a small perimeter loop, for example, then it would flag up that it was the resistance was too low. And the easy way to resolve that is just to use a thinner gauge, either copper tape or wire, which will increase the resistance as a result. And then finally, you will get another message, which is an impedance error. And this is again where it's not where you get the ground fault, where it's actually the loop is actually physically connected to ground. This is one that you would get with the induced ground fault, where there's not actually any physical connection between the loop and earth, but the induced currents from the magnetic field that's being produced by the loop is causing these small currents to kind of provide or produce an earth kind of feedback to the driver, and this is what this will show up as a result of that. So for the V plus series drivers, remember we were mentioning about what was the maximum resistance that could be applied to the loop before the driver showed an error. These are the values for the V plus series. So you see, for example, for the V7, which is our smallest driver, the value is only 6 ohms. And then it's 12 ohms for the V15 and the V15A, and 24 ohms for the V22. So you can see the higher the voltage capacity of the driver, the higher the resistance is. And effectively, that's everything covered. Are there any questions from anybody regarding any problems that they've maybe encountered or any experiences that they've had that they maybe want to share with the rest of us?
Yes. James, this is James. Can you hear me?
Yes, I can hear you, James. Yeah.
Okay, and I'm going to speak to Dave. So, Dave, one of the things I didn't see covered in here today is that you could lay your perfect loop, phase array, everything is great. When you plug the V22, you plug the V22 into the wall socket in the church, and you get two red crosses immediately. Unplug it, they go away. The fault error is in the building, not in your loop and not in your driver. Yeah, it's the way the building wiring was, and the way that we actually narrowed it down. You didn't see it in the V34, you didn't see it in the V15, you didn't see it in the V7, but you see it in the V22. And Dave, you and I talked a lot about this. So we ended up taking a standard, that's a 3-prong plug, and you cut one of the grounding prong off, and you plug it into a 2-prong plug, and you plug it in the building, and the V22 works fine. And so you go to the church and you say, listen, you got a problem. You go around to the wall sockets, and they all have a grounding fault problem in the whole building. And ends up in that unit's still working today, 4 years later, with that 2 prongs in it. But we're not into the wall anymore. We're going into the rack power source, which is a lot cleaner. Still using the 2 prongs. So I don't know if you recall that. It was about 3 or 4 years ago. But we couldn't get the V22 to come up. Just come up with red X's on there. That was it. But the fault, I mean, we followed everything. We pulled everything out of the wall. We pulled the carpet up. We went over all wire. And it was, the driver was very sensitive to the wall socket. I can't recall exactly, but I think it had to do with the way the building was wired.
Well, older buildings like that have the neutrals and grounds all tied together in sub panels throughout the building. And what you're doing is energizing or putting current into the ground. And sometimes it goes to where it's supposed to, the grounding rod outside. Other times it'll take the path of least resistance and go, the driver will see current on the ground, and that's where you get your error. If you lift that ground or remove that ground, it doesn't register that, but it's still not a good situation, but you're bypassing the ground fault detection in that certain driver.
Yep, that's what it was. So we that's the best we could do for that church, but it's still working. It's 4 years. It's great. They're happy. Everybody's happy. And of course, we're waiting for the other shoe to drop, for that driver to stop working, but it hasn't. So,
well, and that's what,
remember, it took us a week to find that.
Right. But that's what happened with the HLD9s and HLD7s. I mean, they didn't have any of that detection, and they worked everywhere, regardless if they were shorting to ground or not. But you're losing current because it's being bled off to ground somewhere, somehow. And, you're just using more current than you actually really need. But in that case, it worked.
Yeah. And when James didn't talk about that today, that's like a 4th one for you when it's in the building. It's causing.
Well, but that varies so much because sometimes they have parishioners who change an outlet and they don't know black from white, so they just connect it to the screws, and now the imbalance of the current coming in the building is feeding anything metal in the building, is carrying that current. So if you plug any electronic device into it, the ground has current in it, and it's not supposed to.
Well, I just wanted to mention that because it was one of those problems that took a week to solve because we didn't know anything about the building, but we do now. We know a lot about it. And I also want to say that when you're laying your loop, if you're staying one step ahead of the ball game, you're not going to get, when you cross wires, if you've taken that into consideration, if you've taken the metal studs, you got to be thinking ahead when you're laying that loop in. You can't. It's a tough situation when you lay the loop and turn the driver on, and you get fault grounding errors. You should be thinking about that every step of the way. You should check the wall sockets out. We put our Our sniffer, we always keep it in the ground of the wall socket. You know, you don't just hook it to something. We got a plug that plugs into that. So that sniffer stays right there at that wall socket. And we just use, our loop wire to go around and do what you do, punch holes in the flat wire all the way around in sections. And we've taken the wire and cut it purposely in sections, in quarter lengths, all the way around the church, in a multi-loop, till we found the section that didn't work. Because we can solder those sections back. But we did find it, it turned out to be right dead center. And what it was it was on the seam of the carpet, and some child or somebody had dumped a Coca-Cola there. It was a 10-foot circular. The carpet wicked the Coca-Cola down onto the wire. So there's two wires in there, two 14-gauge wires that are covered. That Coca-Cola ate right through the vinyl tape, ate right through the wires, ate right into the concrete, and ate the sealant off the concrete in a 10-foot circle. And you could touch the wire, and it would just brittle, just almost turn to dust. And that took a week to find. Because what was happening was they were connected, and only when the carpet was slightly moved did you get the fault. Like, somebody would walk by and it would separate, and then it would go back. And so the carpet guys had to come in, tear up the carpet in there, and we had to lay two 20-foot sections on flat wire, soldered in. But yeah, it was right dead in the middle of the church.
Thanks for that, James. That's brilliant. Any other questions for anybody else?
Yes.
Klaus? Hi, Klaus.
Hi, from Denmark. I'm especially installing in church in Denmark, but it only existing loops in the floor, not accessible. And I earlier used a lot of V7, and I had a problem that there was no ground in old church. And I often get a loop ground fault. But if I restart the driver 4 or 5 times, suddenly it says loop good. And then I tell the church, don't turn it off. Some cases I can tell the church to get an electrician and to make a ground installation, and that helps. But I don't understand why, because it's operated with a switch mode power supply with, I guess, 12 volts. So I can see the driver can see the ground.
That could be a couple different issues. That could be temperature or humidity. If it's flat wire, we've seen it to
It's
where...
never flat wire.
Oh, it's round wire?
Yes, always.
Okay. Well, yeah, that's hard to explain. It's either inducing somewhere, and based on, I don't know, sometimes temperature has a lot to do with it, or humidity. But restarting the driver, that seems odd that it would be good at one time and not others.
V15 has not the problem.
Okay, so the V15 driver, you don't have that problem. Is it the V Pro drivers that you have the problem?
No, it's just V15 or V7, but I'm almost never use V7 anymore. I don't remember 14. I can't remember if there was any problem with V14.
Sorry, Klaus, I think we were losing you there, just a poor connection. Maybe I don't know if you want to recap what you'd said there, just the last 30 seconds or so.
Yes. V15, I don't get the loop ground fault, only on V7. But and it's the same with an external power supply. So I can't see the difference, but there's no problem with V15.
Well, the V15 has a 24-volt power supply and the V7 has a 12-volt, so that might have something to do with it, either impedance or inductance or something with not having quite enough power on self-startup or something. But that does seem odd that you get that error regardless.
Yes. Yes, you can't switch power supply.
No.
Yeah. And just Klaus, just to clarify, this has happened with a number of different V7 drivers.
Yes.
Yeah.
Yes.
Mhm.
As yesterday. So it's I'm installing a couple of drivers every week.
Yeah.
We have a lot old drivers from Transit who is worn out. So I'm shifting one or two every week.
Okay. Thanks for that, Klaus. Are there any other queries or questions that people have that are on the meeting you'd like to ask? Let's have a little look at the chat. Hi, Timo. I'm just reading your message regarding the use of it sounds to me that it's like a direct burial cable that's been put into the concrete. Is that right? What issues are you getting regarding that type of installation? Are you able to elaborate on that for us? Just to say, I'll just say what the chat message said. It says, we do not use carpets anywhere. The loops are not possible to fix afterwards. They are sunk into the concrete. So there could be a number of issues there. It's possible that there's maybe been a cut in the loop where they've maybe installed seating and drilled through it. There could be a short if it's a phased array for a similar problem. If they've not used proper direct burial cable and just used ordinary PVC covered cable, then perhaps the concrete has eaten through the insulation and caused problems there.
Wire sunk in concrete, that's pretty much, that's 80% of what we do. We cut and put wire in concrete. And so we come across a very small number of problems. And you can put the wire in the concrete and cover it with the carpet. And usually the problem is clear. Somebody has drilled into the concrete, or some other vendors come in and pounded a nail or took one of those shotguns and put something into the wire. So it's obvious it's got to be fixed. So the first thing is the warranty is voided. Number two, you dig the wire out and you can't at that spot, but you can't dig it out everywhere. So you have to run a flat wire. Well, you just pull it up out of the ground, out of the concrete, seal the hole. Now you've got two ends of the wire sticking up. You're going to have to solder a flat wire there and lay it like it's a flat wire under the carpet or on top. And you're going to show that to the customer. You know, it's going to cost them a lot of money, you know, $2,000 or $3,000 to do that. But they voided the warranty. They get the loop back. And now they got a section, you know, a 3-4 foot section of flat wire. We had a place where a guy drilled through all of our phased arrays with the, he drilled through the concrete on the steps to put the handrails in. That big around, diamond. And so every time he went through the step, and we came down the steps, and each of the steps have been cut and sealed with the phased array wires in there. So, you know, on the ends, you've got 4 wires, not just 2, but 4. So you got 4 round wires coming, cut them and put them in the steps. But somebody told him that that Ardex line, when we sealed it, was his line to put the posts in. So he started drilling each step, putting the post in, and when he pulled up the core, you'd have 4 wires sticking out each side of the core like this. You know, see, they'd be sticking out. Here's the core. All these wires would be sticking out like that. And he got through 3 steps before somebody stopped him. So we just ran flat wire, sealed it all up, ran flat wire up those steps, sealed them on top with the vinyl tape. We use the same stuff that Dave does, and wrote a letter, made them sign it, voided the warranty on that phased array in that area. I mean, we had 18 phased arrays in this place, 18. And he got the toughest one to work on, all the way up in the nosebleed section. At the very top, he cut the 3 steps. So there were 4 flat wires laid on those steps we can cover. And then, of course, they got their poles, we got the carpet in. But in concrete, you just, you know, rarely does it ever happen that you don't know about it. You know, somebody's either drilling a seat bolt hole. We had that happen, and void the warranty in an opera house. The guy just came right in and put it right through the wire, but you could see it. There wasn't anything hidden or broken, or the wires hadn't been eaten away. I mean, because you have to lay a complete wire. You can't solder concrete wire and put it down into concrete, because it will get eaten away. You'll dig it up and it'll look like white dust in there. You won't have any continuity at all. So I wouldn't worry about pulling the carpet up or digging a wire up if you think it's there. You know it's there. I wouldn't do it if you don't know it's there. But if it's obvious, do the work and show the customer and charge for it. I mean, I don't think we charged that customer for the 4. I think we charged them $12,000 to fix that 3 steps. Because it took 2 guys sitting there soldering, laying it, stretching, pulling the flat wire, and all the work. I mean, it took a couple of hours to get that done. So you can fix it. But don't be broken hearted.
Thanks for that, James. Thanks for that, James.
Yeah, just look for and make sure they tell you. You know, when I go into a job, I don't know if you guys do this, but I show them a piece of paper that says, you cut this wire, or anybody cuts it, it's $1,000 on flat wire. It's $2,000 on a round wire to fix, just to start. That's just the cost. That's not my labor time. And I show them. I said, so let's protect this wire. We put signs out. They still do it, and you guys know it. If it's a flat wire, it's going to get cut by a carpet cut. You know, he doesn't care. And we've gotten a check from a carpet company for $22,000. $1,000 a cut. He cut the carpet 22 times, the wire 22 times.
Mm-hmm.
And he was crying. He was crying writing that check. But we really worked hard to tell him not to do it. We literally put wood over every place the carpet was going to go. We put a piece of wood that says, do not cut this wire, and we taped it down. And they removed the wood, cut the carpet there and the wire, and 22 times. So they are hard-headed.
Yeah, it could be an expensive business, rectifying, faults like that. Yeah, it's a good point that you make, James. And I'm quite sure there's a lot of installers that can sympathise with what you're saying. Anybody else that has any queries or questions? Dave, is there any last beads of wisdom that you want to share with us?
I think we've covered it.
That's good. That's good. We're having sort of like network sort of reliability problems here as well. So I'm not sure how long the connection is going to remain reliable. So maybe it'd be a good time to terminate the meeting. If there's anybody else, this is your last chance. If anybody has any questions that would like to share with us. Okay. Well, if not, what I will say, I just want to just quickly remind you that there's going to be the next webinar. We're going to be discussing. It's going to be loop systems in transport. So that's going to be quite an interesting one. This is going to be when we're going to talk about installing loops in, taxis. We've got a good case study that our Spanish distributor has done, where they've installed a lot of loop systems in taxis, which it works very well, and also in buses. And buses are a far more challenging environment, and it's certainly something that can be done. It's doable, but there's a lot of kind of like research and work that needs to go into it before you can finally go ahead and do an installation. So we're going to cover that. So that'll be that's our next webinar, which I hope you'll be able to join us for. So without further ado, I'll let you away and enjoy the rest of your morning or your afternoon, depending on where you are. And we'll look forward to seeing you again soon. Okay, thank you very much.
Nice. Yeah.
Thank you. Dave, have you gone already? Oh. Hey, Klaus, I was hoping Dave would stay on for a second. That's all right. I guess I'm going to leave too. Klaus, have a good evening.